Ve şimdi de yine sunumunu gerçekleştirmek üzere sahneye Janne Paananen'i davet ediyorum efendim.
Okay, good afternoon everyone. Janne Paananen, Data Center Systems Architect from Finland. And I'm here to talk about on very technical challenges what relates to data centers for the grid and how the data center can actually be a good grid citizen and going through those aspects. Now, Finland has been mentioned today for a few times, and besides of nice climate for data centers and cheap and clean energy, Finland also has other things to offer. For example, excellent engineers and a state-of-art manufacturing facility for critical infrastructure. Eaton has a new large factory close to Helsinki Airport where we manufacture our UPSs and especially the large UPSs for our global customers in the EMEA region and the regional customers, and are at the moment delivering lots of those for the large ongoing projects, for example, in the UAE. And besides of the manufacturing, then in Finland we have all the key functions for the UPSs, starting from product development, product support, all of those things. So it's the kind of knowledge center for the three-phase UPSs in Europe, serving the European market and global customers. Then to the actual topic. So data centers and the energy usage. A few years ago, International Energy Agency was kind of forecasting flat energy growth for the data centers. In recent numbers, it's growing again. And the latest estimation for 2024 was that globally data centers will consume 400 terawatt hours of energy. But having downloading the sustainability reports of certain data center companies, these 5 data centers alone consumed last year 100 terawatt hours. And then you are missing some of the biggest players and you are missing all the Asian data centers and most of the market. So I would say that the 400 terawatt hours from the IEA is a gross underestimate. Actually, it's more. If you compare data center companies and how much they consume electricity, they are consuming it more than many of the countries, nations. So they are massive energy, electricity consumers. And then on the right side, if you check the comparison, I mean, just recently there was discussed 500 megawatt sites, 1000 megawatt sites. If you think about the data center campuses that are several hundred megawatts to thousands of megawatts, they are like large cities, like metropolis. So they have a significant local impact onto the grid, but they are in just a much smaller geographical area. When talking about the energy use, digitalization, everybody is pointing finger always on data centers, but then bottom right as an example on the energy consumption of one of the large mobile phone network operators. And you can actually see that the mobile networks are consuming more power than the data centers. So digitalization is not only about data centers, it's also the communication networks, especially about mobile networks. Okay. From global greenhouse gas emissions, 1/3 or more of that one is actually coming from the industry. It's manufacturing and transportation of materials and goods. That's 1/3 of all the emissions. We are creating too much emissions because we are over-consuming. And here's the funny thing, as an engineer, whenever you have a problem, the solution from engineers is that, oh, let's build something new to solve this problem. But it's building the new that is causing the problem. So alternative way of thinking about solving this problem is, can you leverage existing assets and use them smarter to solve the problem? And here's a comparison of BESS system battery energy storage against data center power infrastructure. And they are strikingly similar. So instead of providing all the grid services from dedicated, purpose-built BESS systems, you could take lots of that flexibility also from existing assets like data centers. And that can you bring lots of savings in the cost, but also in the embodied carbon. So it's a green thing, nice thing to do. I have been working with grid interactive technology and UPSs for the past 10 years. And we've had customers who have been using it since 2019. So it's not a new thing. But with modern power electronics and like a modern UPS, you can actually flexibly manage how much power you draw from the mains, how much you take from the batteries, and you can provide flexibility and services. You can provide fast frequency regulation and the ancillary services. You can make local energy management. You can support on-site power generation. You can also do other things like filter the fast load variations and harmonics, and then in the future things like complying with the new grid regulation and so on. So a modern power electronics like modern UPS is a very flexible asset when you program the correct functionalities into the product. Sometimes people ask that what is the value of grid interactive UPS and so on, and why you should be doing it. This is an example calculation from Ireland, made by Baringa. And then I have a couple additional links where I'm kind of calculating this out and what does it mean. EirGrid, the Irish grid operator, has said that if you can increase fast frequency response from flexible loads by 400 megawatt, it allows you to reduce your system inertia floor by 8,000 megawatt seconds. 8,000 megawatt seconds as a spinning energy equals 1,600 to 2,000 megawatts of spinning gas turbines. And during the windy conditions, they are running those with 20-30% load levels. So if you can reduce the inertia floor, you can take that capacity out from the grid, stop burning the gas, and use more wind. So you don't curtail wind, and you retire the gas turbines. And when you calculate the annual emissions and how much you save on annual and a system level, then when you allocate that, it can be up to 4 million kilograms per megawatt of UPSs. Well, what does it mean? Typical life cycle emissions in Ireland for a megawatt UPS would be 800,000 kilograms. So the UPS comes carbon negative in 2 months. Or if the same 1 megawatt load is using the average emission factors, it's creating 2 million kilograms of emissions per year, the 1 megawatt data center load. But when it's providing the services, it can help to reduce the system level emissions twice as much. The thing is that when we are evaluating what is smart to do and not, we need to understand the big picture and not focus on a PUE, this one, and trying to tweak things and so on. If you improve a UPS efficiency by 1 full percentage point, that's a lot from technology perspective. But by providing ancillary services in Ireland, your annual impact on the system level emissions is 100 times greater than by improving UPS efficiency by 1%. So you shouldn't be focusing on the PUEs and so on, but seeing how you can help the system to decarbonize and so on. It's all in those documents if you want to translate and read it. Okay. So grid interactive data center, great thing. You can support the grid, more renewable, greener system, less emissions, cost savings, all of those things. The main topic today is really the new challenges for the electricity grid. When you have a several hundred megawatt of site, and the way it's behaving, it can have a significant impact for the grid reliability. And especially when you have lots of those big sites in a small area, they can pose a serious risk for the electricity grid. So I'm using Dublin as an example. That thick white line is the 220 kilovolt grid around the Dublin. And then the data centers, roughly 20% of the Irish demand, is all connected to that grid. Very small, lots of capacity, and so on. And now, here's the problem. So the green one is the voltage in the high voltage grid, 110, 220, 400 kilovolts. Red one is the output of the generation, and then the yellow one is the UPS load. And this was supposed to be animation, but it's not, so I will explain it. So in the beginning, when you have a normal voltage, you have a normal power generation, you have a normal demand. Everything is balanced. If you get the fault in the grid, and the high voltage grid goes down, then the power generation goes down because there's no grid. But the demand goes down as well. And during the under voltage, no generation, no demand. But for all the power generation that you connect to the grid in all the countries, you have a so-called fault right-through requirement and post-fault active power recovery. Meaning, when the protection devices have cleared the fault from the high voltage grid and the voltage recovers, then the power generation will restore their output immediately. And they will restore their output power to pre-fault level. And they try to do it. Now in areas like Ireland, Virginia, Texas, and so on, where you have lots of data centers and large units, the problem is that the data centers will trip off from the grid. And when the power generation is trying to restore their output power, there is no demand to taking the energy. So they will produce too high torque on the shaft, and the generator speed goes up, frequency goes up, voltage goes up, and if the frequency goes up too much, then all the power plants will disconnect. And then it's game over. No more grid, no more power for anyone. What is needed is to specify that when you have large electronic loads, how they behave, how large data center campuses are behaving in a grid. This is not a problem for Ireland. There's multiple transmission system operators who have identified the same problem. And those are AMO in Australia, ASO in Alberta, Canada, EnergyNet in Denmark, EirGrid in Ireland, ERCOT in Texas, Fingrid in Finland, and RT in France. And all of these have published new technical requirements for data center power connection, or have proposed new requirements, what needs to be done. And like last year in Virginia, there was near-miss incident when there was a problem in a high voltage grid with the surge arrestor, so little blip in the voltage, and 700 megawatt of data centers disconnected. And it almost took down the whole eastern part of the USA. So this is the problem. And that's why you have the new requirements coming on for fault right-through and post-fault active power recovery. Also, with the new project, there's more focus on the harmonics. So we as a supplier need to already provide for certain countries detailed information about our harmonics, interharmonics, harmonic impedances, flicker data, and so on. So all the same data that's been traditionally asked for the BESS systems and wind farms, now as a UPS supplier, we need to provide the same information. And last but not least, we also need to provide PSCAD, so electromagnetic transient simulation models of the hardware, and the RMS domain, PSSC design, and so on. And with these simulation models, then the transmission system operator can verify that how the data center is reacting with the power generation, wind farms, and other assets in the grid before they are connecting it. And verifying that you don't get any harmful voltage variations, fluctuations, frequency fluctuations. You don't get inter-area oscillations or the subsynchronous oscillations like happened in Spain and so on. So you can verify that the new large facilities connected with all the power electric loads do not start to wrong way behave in the electricity grid. And this is all new stuff that the data centers need to understand for the future. Okay. For your courtesy, I have mapped out and drawn in an Excel the new proposed requirements for the fault right-through. The green area is the allowed operating voltage range according to the ITI CBMA curve for the server power supply units. And then on the left end, you can see that there is a very, very narrow green band. So the standard saying that the server power supplies needs to tolerate under voltage for one cycle, 20 milliseconds. But the fault right-through requirement is typically for 150 or 200 milliseconds. And meaning that if the under voltage in the grid is shorter than that time, when the voltage comes back, you need to restore your demand immediately. Bad news for the crypto miners. They don't have any UPSs, they cannot comply. Meaning in the future, they don't get the connection permit unless they change their designs. Bad news also for some other technologies and so on. So the nice thing is that if you use traditional data center designs, if you use double conversion static UPSs, implementing this functionality for a modern UPS is trivial. A standard UPS nowadays, like one from Eaton, if you have short outage, it will drop on batteries. When the voltage comes back, we are purposely keeping the UPS 5 more seconds on the batteries. Why? Because if it was a generator coming online and starting to feed the UPS, we let the generator voltages to stabilize. And then we use a slow ramp to get the power up. But for the grid, for this fault right-through, it's too slow. So now we need to make a logic that during the under voltage, we start a counter. And if it's a short outage, then when the voltage comes back, we minimize the delays and we get the demand back to the grid as quickly as we can to maintain the balance between demand and generation in the grid. But if the outage is longer, then we can act as today. Rather easy to do, but then if you have some other technologies like line interactive UPSs, rotary UPSs, or no UPSs at all, then it can be much more challenging to meet those. The other important aspect is that white area there on the left, saying power sharing down to 50%. So if you have a fault in a high voltage grid, and at the location of the fault, voltage can go to 0. But you can still have a severe under voltage hundreds of kilometers away from that 220, 400 kilovolt grid. So often with these faults, the blast radius is geographically very large. If we allow the UPS to tolerate momentary under voltages and stay online for lower voltage, let's say to 0.5 pu, then we reduce the blast radius and we keep the system more stable. So these are rather simple changes that is rather easy to do to any modern double conversion UPSs. And we are demonstrating these changes for 2 TSOs and a customer next week Friday in Finland, and so that's what we have developed. So we are ready with this one and then for the next year. One slide about the AI loads. So I'm not sure if anyone else has mentioned it today, but AI loads are a bit different than the typical traditional data center loads. When you are performing machine learning, you will have your GPUs processing and calculating, then they will stop, save the data, reload algorithms, parameters, and then repeat. And on machine learning, you are repeating these cycles. And this is what you are doing with the large language models and so on. And every time you start the computation, you will get the power spike, then you stabilize, you stay there a second, 5 seconds, few minutes, who knows, depending on the algorithm, and then you have a short break and you will start again. So you have very high power variability and fast variations. Microsoft, NVIDIA, and OpenAI just recently published a very good white paper on what you can do on the servers, how you can have on the GPU so-called minimum power floor, and how you can use in the future the power shelves with local energy storage to filter out some of those variations. But something is still maybe remaining. And then you also have other GPU providers like AMD and so on. So on the bottom right, you have the red what the GPUs are taking. And then as close to the GPUs, within the racks or next to the racks, you should have fast filtering that is taking out those fast variations. And that is then helping to fix the load so that it doesn't cause issues for a backup generator, for the grid connection and so on, doesn't cause flickering and power quality issues. So then you result this yellow one. But then if you have a site of hundreds of megawatts, and if you start really large GPU cluster, you have 20,000 GPUs doing large language model. When those are starting up, it's possible that you will connect 30 megawatts to grid like this in a second. And that very fast power variation can be too much because you are momentarily losing the balance between the demand and generation. And then you activate your primary reserves for the frequency regulation and so on. And the grid operators don't like it. So on the grid regulation for Finland and Denmark, they are recommending that the data centers can ramp up their power maximum 50-60 megawatts per minute. So they don't want that the really large facility is just turning on the power and off like that. You need to gradually increase the power so that you maintain the stability and frequency stability in the grid. And a similar thing in Texas, they were recommending 10 megawatts per second. And for that one, then you need to have the second level filtering with batteries and so on that you can use to control the ramp rate of the power in the beginning and at the end of the training cycle. And that's how you then avoid causing any serious problems then for the grid. So this is more challenging than with AI loads and so on. Okay, so if you are lucky, if you are using double conversion UPSs or medium voltage solid state transformers like in the right, when you have a converter systems that are in series between the grid and the load, you can easily do the fault right through filtering, managing, and making a grid-friendly data center. But if you are a crypto miner or doing something without the UPSs, or if you use rotary UPSs, line interactives, and so on, then you might have much more challenges on how to do it, how to filter brownouts away, and all of those things. So it's a design question. How do you want to design your data center so that it will fulfill the future grid regulation? Now I will conclude and save you from agony. So to summarize, a data center as a good grid citizen, first point that I didn't touch, but what we do a lot in Finland, is that it efficiently recycles the waste heat. In Finland, the #1 site selection criteria is the availability of district heating network so that you can actually reuse the waste heat from the servers and feed it then as a heat for the houses, warm water, space heating, and all of those things. Okay. Second important thing is to provide the flexibility and services. Like I explained the Ireland case, that if you can support higher penetration of the renewable energy, low carbon energy, and help to reduce the emissions on the system level, then decarbonizing the electricity. The first point is decarbonizing heat, then helping to decarbonize the electricity. So that's important. As a third, with the modern UPS, you can then provide services like the under-frequency load shedding and various things that can help the grid during the most severe disturbances. When you lose large power plants, data centers can provide the immediate fast response to reduce the demand from the grid and make the grid more reliable. In Ireland, when they have been increasing their share of renewables all the time, they have more frequency variations than in the past, but they have also increased the fast reserves fast frequency response. And because of that one, the frequency variations are much smaller than in the past. So the fast response from power electronics loads, flexible loads, can really help to keep the frequency in control and help. And then last but not least, what I was speaking as last, data center should not negatively impact the power quality, stability, or the reliability of the electricity grid. If you have a neighbor who is throwing the trash on your yard and saying it's your problem, you don't like it. If you have a data center that is causing issues for the grid and saying that's your problem, you don't like it either. So if you are causing the problem, then you need to find a way not to cause those problems and not saying, oh, that's for the grid to figure out. And that's what we often hear from data centers, that if they are causing problems for the electricity grid, then the grid operator needs to find a way of doing it. And then the grid operator will go and install and spend lots of money on building best systems and so on, and increasing the cost, emission, embodied carbon, and all of those things. And same time, those best systems are eating away the connection capacity from the data centers, so you can't connect that many data centers. So, smart designs, correct technology, and everything is possible today with modern UPSs. Thank you.